Hello and welcome to Build Your Own CPU Part 2. In this video I shall be talking about the MOSFETs I used, the problems the body diodes cause, how CMOS works and some ways it can be used, how the clock and pulse timings work, and how I made a memory cell for the registers using as few transistors as possible. MOSFETs come in two flavours, enhancement mode and depletion mode. The ones I used, shown here, are enhancement mode. There are N-channel and P-channel types. If we just look at the N-channel MOSFET for the moment on the left, the top leg is called the drain and is connected to the positive side of the circuit, so the current can drain from the supply above into the transistor. When the junction is turned on by raising the voltage on the gate, then the current will flow through the MOSFET to the source leg, and this will source current into whatever it's feeding. To make the junction start conducting from the drain to the source, the voltage on the gate, in reference to the source, known as VGS, must be above the MOSFET's threshold voltage. The N-channel MOSFET, I chose the BSS138, as it was the cheapest SOT23 MOSFET I could find. It has a current rating of 220 milliamps, as we can see further down here, for continuous, or 880 milliamps for pulsing, which would be much more than enough for this project. When you come down here, we've got the VGS. Now typically it's 1.3 volts, but can be as high as 1.5 volts. That's just its start to turn on voltage. If we scroll further down to the other charts, we can see here that the VGS, gates to source voltage supply, really needs to be above 2 volts, preferably about 3 volts. So this could be important in the circuits later, so remember that. The P-channel MOSFET works in a similar way, except the source is the positive leg and the drain is the negative. The gate voltage must be lower than the source for the junction to turn on. For the P-channel MOSFET, I chose the BSS84. Here we have a current rating of 130 milliamps, and notice it's negative because it's P-channel. And yeah, it's 130 milliamps, but it can pulse up to half an amp. And this one has got a VGS of minus 1.7 to 2 volts. So not as good as the N-channel. P-channels generally are not quite as good, but that should be fine. If we go down to the chart for this one, slightly different. There we go. We've got gate voltage to resistance this time. We really need to be above 2, or more than minus 2.5 volts on the gate source to get that one to switch well. Again, pay attention to that will come up later. There is a period when both MOSFETs are turned on. When the data coming in on the left is above 0.8 volts and below 4.2 volts, in this instance because we've got a 5 volt supply, both minimum VGS's thresholds are met. Thus, both transistors conduct, shorting the 5 volt supply direct to 0 volts. This is where the CMOS circuitry uses its power. You need to switch this signal as fast as possible. What I've done on all my boards is install a 100 ohm resistor in the supply to any circuit to limit the current to a maximum of 50 milliamps in case something goes wrong. These MOSFETs can easily handle 50 milliamp all the time, so this should keep the magic blue smoke in. We need to switch data on and off the buses, so we don't know if we are switching at 1 or 0. In this case that's 5 volts or 0 volts. This is a commonly found circuit to enable switching. Imagine there's 5 volts at data A and 0 volts at data B, and the control signals are off. Then the MOSFET N is not conducting and the body diode is against the flow, so the voltage can't get through. Now imagine there's 0 volts at data A and 5 volts at data B, and the control signals are still off. Then MOSFET P is not conducting and the body diode is against the flow, so the signal still can't get through. Now, if the control signals are on, then the voltage can flow from data A through the N MOSFET and the P MOSFET body diode, or flow from data B through MOSFET P and the body diode MOSFET N. It all looks good, but there's two issues. Firstly, you need to invert the control signals for the P-channel MOSFET, which takes more transistors. And more importantly, you're relying on the forward voltage drop of the body diodes to be low. These are not normal silicon diodes and can be between 1.5 and 2 volts. Thus, your data signal of 5 volts is now 3 volts, which is in the middle of the switch on voltage of the gates and can cause indecisiveness. Thus, the gates may not switch as intended. This is the way I decided to go. When the data enable signal is high, the following will happen. Imagine data in is at 5 volts, i.e. logic 1. Current can flow from data in via diode 1 through MOSFET Q1 to data out. As data in is 5 volts and data out needs to be set to this voltage, this will give a voltage of around 4.35 volts at data out, well into the logic 1 voltage range and above the turn-off gate voltage of any P-channel MOSFET further down the circuit. If the data coming in is a 0, then data in will be 0 volts and data out needs to be pulled down to this. So if data out was at 5 volts, then this will get pulled down via Q2 and D2, and the voltage at data out will be no more than 0.65 of a volt, which is below the turn-off gate threshold of any N-channel MOSFET being fed. We only need the data in enable signal as well, so there's no inverting, no extra transistors. Of course, these diodes should be switching diodes. I used 1N4148. Now let's have a look at some CMOS gates. This is a 2-input AND gate in CMOS. It is made from a 2-input NAND gate plus an inverter, or NOT gate, whichever you want to call it. Notice that in the NAND gate section, the 2 P-channel MOSFETs are in parallel and the 2 N-channel MOSFETs are in series. When both A and B are off, we get 0 output. Q2 and Q4 will be turned off, and Q1 and Q3 will be conducting. This will put 5 volts onto the input of the NOT gate made by Q5 and Q6, giving a 0 or 0 volts output. With just A on, we still have a 0 on the output. With just B on, we get the same. But with both A and B on, we get a 1 on the output. This is an OR gate. You may notice the P-channel and the N-channel MOSFETs are swapped configuration. The P-channels are in series and the N-channels are now in parallel. With A and B off, we get 0 output. With A on and B off, we get a 1 output. With A off and B on, we also get a 1 output. And with A and B on, we still have a 1 output. Now's a good time to look at the clock timing. Here's the timing pulses generated on the motherboard. You can see the microcode clock stepping along and the pulse to the right. You'll get clock, pulse, clock, pulse, clock, pulse, and this carries on through all 16 steps. This is the timing of the clock signals and the pulse signal. The CPU is designed to run off 16 microcode cycles per instruction, but actually just uses 13 of them. This is equivalent to 8 cycles per instruction, as 5 of them are used to increment the program counter, as we'll see when we get to that part in a later video. I chose a fixed length instruction as it was just easier. If you use a ROM chip or a diode matrix for the instruction decoding, then variable clock cycle length instructions is easy. Using a transistorized or diode matrix would be very large, so I'm using logic gates to reduce the transistor count, as we'll see in the instruction decoder video later. So we have what I call T states, T0 to T15. T0 is the same for every instruction. It is the fetch cycle. So imagine that T on is T state 0. T0 comes on. The instruction decoder will enable various control lines to place the instruction from memory at the input of the instruction register. Then the pulse now comes on to enable the data to flow into the register. In reality, the clock and the pulse could go high together. After a short while, to let the data stabilise, the pulse switches low to lock the data into the register. In a rising edge latch chip, you have this arrangement. When the input rises, the output rises for a short period, causing a pulse output. This output enables the data into the register and then locks it in when it falls. So a rising edge triggered gate or flip-flop or whatever is in fact a falling edge trigger internally. The pulse width being the propagation delay of the inverter. I'm doing basically this, but with a separate pulse so I can control it. I use this for single stepping, or I should say quarter stepping of the cycle, or 1/52nd stepping of an instruction cycle. This is very useful for debugging because you can go partially through an instruction and then measure your control signals, etc. to make sure everything is flowing in the right direction. We'll see this in a later video. After the pulse has fallen, we'll then wait a short while to ensure that the data stays stable as it's latched in, then the clock can go low. I've since found out this is exactly what the 6502 microprocessor does. The data must stay valid for 20 nanoseconds after the fall of the phase 2 clock. Phase 2 clock being the pulse signal. The off period of the clock does not have to be the same length as the on period. It only has to be long enough for the control signals to turn off. This clock cycle is the same for all T-states. I'll cover the T-states in the instruction decoder video. Here back on the motherboard, we can see the T-states turn on and off one at a time, and the pulse activates between them. T0 to T6, T8, T12 and T14. T7, T13 and T15 are not used. T10 does not light because the LED is dead and it's really hard to solder, so I just didn't bother. This is one of the register PCBs. Up here we've got the supply coming in, 5 volts and 0 volts, feeds down to the next card. Over here are the control signal inputs. There's a reset one there, and there's a output enable, input enable, and the pulse. Over here is a decoupling capacitor to smooth this supply coming in. Here is the all-important magic blue smoke resistor, which feeds the supply down to the rest of the circuitry, and there's another decoupling capacitor across that. Over here, these transistors, they're just for feeding these LEDs up here so we can see what's going on inside the circuit. Over here, these 6 transistors make up the AND gate for the register input and pulse signals coming in to switch on these clusters of transistors, which are the actual memory cells. You can see here these are the diodes that and the feedback resistors that feed the signal into the memory cell. So these will be the 2 NOT gates of the memory cell, and that would be the feedback resistor. And these 2 diodes feed into these 2 transistors for the actual input, and this is the MOSFET for the reset, and these are just 8 of them the same. Now the output is all fed by all these transistors, so there's 4 per bit. And this is tri-state, so 2 of them switch on the supply to the other 2 which are actually switching the signal. And these ones up here are inverting the signal, for one for the NMOS transistor and one for the PMOS transistor. And we can just use that to feed all of them. Now here, this is the data bus in or out. So they feed out to the data bus and they can feed into the data bus. So we can isolate the data bus from this card by these transistors and these few here. Now you've heard me talk about the R bus. Well, that's this bus running down the back here. And that feeds across whatever's on these, comes out of these ports here, and they're active all the time. Also comes out of this port and this port, and they're all identical. That one just feeds upwards, that one feeds downwards, and that one feeds sideways, depending what cards it needs to feed, if any at all. Let's have a look at a register, or more precisely a memory cell, or one bit of memory. 8 of these making a standard register. This is a logical diagram. The physical circuit is a little different. The memory cell consists of 2 NOT gates, U4 and U5, fed in a loop. The output from the second NOT gate, U5, is fed back to the input of the first gate, U4, by a 100k resistor, R1. This holds the memory cell in a given state. This is basically the actual memory made from 4 transistors and 1 resistor. To set the state of the cell, the input to U4 is pulled up or down, and then the small current supplied or sunk by the 100k resistor is overwhelmed and forces the memory cell into the state of the input of U4. The input to the cell is connected via a tri-state buffer U2 that feeds the data bus signal to the input when it is enabled. The AND gate U1 ANDs the register input enable and the pulse timing signal together. When both of these are present, it enables U2 and the data bus is connected to the input of the memory cell. When the pulse signal is removed, the data is locked into the cell. The input to the cell was also shown as connected via a tri-state buffer U3 to 0 volts. In reality, it's just an N-channel MOSFET tied to 0 volts. When this MOSFET is enabled by the reset signal, the input of the memory cell is pulled to 0 volts and resetting the register to 0. The tri-state buffer U6 feeds the memory value to the data bus when enabled via the register output enable signal. The connection Q is for the internal register bus, also known as the R bus, that feeds the arithmetic and logic unit. This is the actual circuit for one bit of memory. These 6 MOSFETs are the input control gates. This is only built once on the register and it feeds all 8 bits. These 2 MOSFETs and diodes are the input control. This is the actual memory cell made from 2 NOT gates and a resistor. This is the tri-state output to the data bus. This is the reset MOSFET. And most importantly, this is the anti-magic blue smoke resistor. Next time, I'll show and talk about the design of the actual PCBs. Don't forget to like and subscribe, and hope to see you in part 3.